Thank you all for coming. If you don't already know me, my name is Tori, and I'm going to be talking a little bit about a really awesome piece of hardware called FPGAs today. And I was relying a bit too hard on my speaker notes, so you won't be seeing a lot of my eyes probably. So recently I was browsing the different accelerated compute instances on AWS, and I stumbled across the F1 family and I saw, whoa, you can get FPGAs on AWS. That's so cool. I mean, I don't know when I'll ever use one, like probably never, but the fact that the option is there in the cloud just really jazzed me up. So obviously I told everyone I knew, but the general response I got was, cool story, bro, but what even is an FPGA and why should I care? So that's why I decided to talk about FPGAs today, mostly so that when an FPGA pops up into your everyday life, you too can get a moment of mild excitement. Okay, so if we consider the compute technology that we have available for processing data without taking price into consideration for now, it becomes a trade-off between flexibility and efficiency. And by efficiency, I'm referring to low latency and power consumption. So generally, the more general purpose your engine is, and the more flexible you are, the more problems and different algorithms you can throw at it, but you sacrifice efficiency. So on the one end of the spectrum, you have CPUs, which under the hood have a control unit which processes some instructions and sends them to an ALU, which is a set of predefined logic functions. And then there's also a set of registers that stores a temporary set of data mutations. So it's all very rigid and set up. Well, yeah, so you can throw a lot of stuff at it, but you don't have a lot of customization over the actual hardware. Then you have a GPU, which is a bit less flexible under the hood in that you can't really run general purpose programs on them, but it's got thousands and thousands of processes that are able to execute jobs in parallel. So they're well suited to a wide variety of applications, but they also tend to be a bit power hungry. And then way on the other end of the spectrum, you have application-specific integrated circuits, or ASICs, like the shoes, which is literally the digital logic burnt into silicon. These offer no flexibility at all, so it does one thing, but it does it really, really quickly and with not a lot of power. So that brings us to FPGAs. They're somewhere between the efficiency of GPUs and the flexibility. It's like somewhere there in between GPUs and ASICs on the spectrum. And I'm going to tell you why. So let's start by understanding what exactly FPGA technology is. So FPGA stands for field-programmable gate array. And I find it's best to say this backwards. So it's an array of logic gates that are programmable in the field. So in basic terms, it's an integrated circuit that designers can dynamically configure and reconfigure to implement their different algorithms effectively in silicon. So the job of an FPGA developer is more similar to a CPU designer rather than a software developer who writes code to run on a CPU. FPGA code describes the digital circuit that is required to perform a certain function, but we'll get to that later. So let's take a step back quick and do a quick refresher in digital logic. So digital logic design is the foundation of all modern processors and boils down essentially to three gates: the AND gate, the OR gate, and the NOT gate. So the AND gate and OR gate takes in two binary inputs. So the AND gate will output a 1 when both inputs are the same. and an OR gate will output a 1 when at least one of the inputs is a 1. And then a NOT gate just inverts its input. So De Morgan's theorem states that these 3 gates can be arranged to create all logic circuit functions. So for example, here's a binary adder function that's made completely out of these gates. You could burn this straight into silicon and it would perform really fast and it wouldn't take up a lot of power. But let's say you put a lot of these in parallel and you do all sort of complex things with them. It's really complicated to design and it's really easy to make mistakes. And once something's burnt into silicon, it's not super cheap to fix. So it can cost billions or millions of dollars to design and then to change once that's happened. So that's where FPGA technology comes in. So the first idea of FPGAs is that they're reprogrammable. And the first building block of reprogrammable technology that was conceived is the lookup table, or a LUT. So LUTs store the output values of some logic gate design in memory, so in these SRAM bits over here. And then based on some number of inputs to the circuit, it outputs the correct output based on the lookup table, essentially, in memory. So here's an example of a 4 input logic circuit where the output is a 1 only if exactly 2 of the input bits are 1s. When an input is applied, the appropriate output is determined, and therefore by setting these values in RAM, you can essentially design any gate or a set of logic and change that in code. So that's the basic building block of the FPGA. There's additional circuitry that's added to this to create the next level up called a logic module. Not really that important for now. And these are referred to differently by different manufacturers. Sometimes they're called ALMs for adaptive logic modules. Sometimes they're called logic blocks like they are here. But yeah, so that's the logic blocks. And the next fundamental building block of an FPGA is what is referred to as programmable routing or interconnects. In ASICs, the routes between logic blocks are physically wired, which makes latency very, very low. But when you program it, it's more, you're more making like a routing table between 2 blocks. And it adds more flexibility with FPGAs, but it comes at the cost of speed. So this combination of programmable logic allows parallelism to the nth degree with low latency relative to GPUs or CPUs, and also lower power consumption. So FPGA configuration is generally specified using a hardware description language, or an HDL. The most common of the two are Verilog and HDL. Verilog is newer than HDL. It's more C-like. But yeah, here's an example of the adder circuit that you saw earlier, but in code, and that's using VHDL. Yeah, so that's the languages. Then reprogrammable technology is not a new concept. It dates way back to the 80s and has come in and out of fashion over the decades as the technology has evolved. So it's obviously gotten better and better over time as every piece of hardware that exists. The first thing that's kind of changed since the beginning is now there's these bigger blocks of memory that are able to store tens of thousands of bits with multiple read and write interfaces, and hundreds and thousands of these memory blocks dispersed throughout the FPGA fabric. Then they've also added something called digital signal processors to speed up some of the floating point math and the matrix math, since this is really difficult to resource intensive and complex to implement from scratch using discrete logic. And then finally, lots of commercial FPGAs these days actually have complete sub-processing systems like CPUs and GPUs, and all the peripherals built right next to the FPGA fabric. So modern FPGA designers have the challenge of finding the right balance between programmable features and the hardened features, like these things that already exist. You really want to benefit from the programmable speed and low latency and low power consumption that you can get from the programmable bits, but you need to still stay competitive with the performance of other chips. So you kind of need to balance between the two. So yeah, modern FPGAs will normally consist of both CPUs, GPUs, network controllers, and other features in addition to the array of programmable gates. So in terms of where you find FPGAs, they're used in a lot of leading edge applications where real-time and low latency and high throughput is required. They're really big in network security, in Internet of Things, high-performing edge devices, medical machinery, cars, and they're really great prototyping solutions. So in universities and research institutions, they're really great. A very exciting prospect is the field of AI, because like Zander was saying, it's in its infancy and it's forever changing, and all these algorithms are really heavy workloads and are super and can be run in parallel. So the requirement for a moldable compute type would be really useful. And then in the cloud, we were turning back to, yeah, Tristan, we turned back to the cloud. They're used everywhere because of the scale of the cloud and the sheer volume of data that has to be moved around. So as an example, Microsoft / Azure, sorry, AMSO, leverages FPGAs for VM accelerated networking and what they refer to as the configurable cloud. So their entire networking structure is based on FPGAs so that they can go and reconfigure it whenever they scale up or change their minds about the different types of algorithms that they're going to use. They also announced in a 2014 paper that their Project Catapult team deployed FPGAs in over 1,000 servers in a data center to facilitate hardware acceleration to ranking calculations for the Bing search engine. And they achieved up to a 95% increase in throughput. So yeah, case studies like these have greatly increased the market for FPGAs and the deployment in other cloud computing resources like AWS. Yeah, so that's it for me. That's my cool little fun fact for today. I hope you guys learned a bit about a new piece of hardware, and you're going to see them eventually in maybe like a toaster or something you open, and you'll be like, whoa, that's really cool. Someone put a lot of work into that. So yeah, that's it for me. Is there any questions?